This video is going to talk about the C development environment on the Linux platform. Most of the video is going to be actually about the compiler, GCC, that we're going to be using, but I'm going to start actually by putting the compiler in its proper context, okay? So what you have on this slide here is a list of all the steps that you would have to go through if you were to develop a C program on the Linux platform in a realistic environment, okay? Meaning like you're not just taking a class on introduction to C programming, you are actually delivering a finalized product that is a C program. So the first step, I guess, is non-technical. It's completely biological. It's your brain. You have to design your solution, okay? Design the program that you are going to implement. So we're not going to cover the tools that are used to do this, okay? This is for the bio classes. Editing is the second step. Once you have an idea of what you want to do, you are going to use a text editor. Okay, I remind you that all the programs that you write, no matter the environment in which you write them, whether it's a REPL, like a REPL Codio online, or if it's an IDE, if it's a command line interface, no matter what you use to actually write your code is a bunch of very basic text files. Okay, so what you can use a basic text editor like Notepad if you want to edit your code, but it's not really convenient. So we generally use programmer-friendly editor in the Linux world, Unix world, and Mac, even Mac OS world. VI or VIM is actually one of those well-known editor. Emacs or Emacs is another one. In our case, you're going to hear also, I need to mention that one because you're going to hear about it. Nano, N-A-N-O, is also very basic. So VIM, Emacs, and Emacs are pretty advanced, actually. Okay, they are still text editors, but they have a lot of features. They are programmable. They have a lot of features. They can have add-ons, etc. Okay, on a Windows environment, you would be looking at Notepad++ or Microsoft Visual Studio Code. Nano is a very basic editor. Compare that to Notepad, okay? Some people prefer to use it because they are more comfortable. There's not that learning curve, to learn VI or XMAX. In this class, we are going to try to take like a middle ground approach. We are going to use something called gedit. And gedit is a text editor. It's relatively basic. It still offers a few like fancy, neat, little features for programmers, like for example, syntax coloring. It's really hard to edit code without syntax coloring once you get used to it. And it has a graphic user interface, very minimalist, so it's easy to learn. You get going with it in no time. I'll show you that in the next video. And that's it. And you can edit your code and prepare those text files. So now the problem is with this step, we have text files that represent the source code, okay? How do we convert that into an executable? Well, that's going to be mostly the role of the compiler. But when I talk about compiler in that step number 3 here, I'm really talking about a bunch of different tools that work like a tool chain together to translate your source code into something that can run on the operating system of your choice. In our case, it's going to be Linux. Okay, so we are going to spend the rest of the presentation detailing pretty much what's happening with the compiler. And in our case, we're using one specific compiler, the GNU compiler collection, GCC. This is what we're going to be using to convert our source code into executable. But there are more steps involved than that. Okay, it's not just about designing a solution in your head, then editing, coding, and then compiling and getting it to run. Okay, the first thing I would point out is, well, most of the time it's not going to work. So this is why we have step 5 here, testing and debugging your code. Testing your code, making sure that it behaves the way that the requirement demands it behave. And then invariably, it's not going to behave always as expected. You're going to enter into a debugging loop. The first way to debugging that we're going to explore in this class is good old-fashioned printf. Okay, so printf is just an instruction in C that allows us to display something on the screen, similar to the print in Python or the println in Java, right? So what we can do is when we run our code and it behaves differently than what we expect, we want to know where exactly it starts misbehaving. So we can add a bunch of printf statements in the code that are going to tell us, okay, this is where I am in the code. These are the value of the key variables, that I'm using. And when I run the program, it's going to output this extra display, okay, on the console, and it's going to allow me to see pretty much what's happening step by step. So this is kind of like the old school way of debugging. Everybody prefers generally to use tools called debuggers. We are going to learn to use one such tool that works at the command line. It's called GDB, okay? GNU debugger, it's part of the GCC suite. And we are going to learn how to use it like very shortly, like a second module or something like that. And that will help you actually track down problems in your code without having to manually insert, those extra printf statements that you then need to remove once you're done debugging, okay? So debuggers can do a lot of stuff to help us, but I would say that designing, editing, compiling, and debugging forms pretty much the basic set of steps and tools that you need to know how to use in order to be able to code. And these are the ones we are going to focus on in this course. But there's more. So I want to at least mention it so that you know where to look, if you want to go a little deeper. And you can always ask me questions, of course. There are tools called static code analysis tools, which allow a program to read your source code. So they work on the source code, okay? And it's going to read your source code and try to warn you against possible errors that you committed. And I said try, because sometimes it's going to detect errors, it's going to report on them and allow you to know, oh, well, I should have done things differently here. Let me go back and edit the code, modify the source code to take care of that error. But most of the time, it's going to give you warnings, okay? Warnings meaning this part of the code is suspicious. There could be a potential problem here. And then it's going to let you review by hand your own code to make sure that there is or there is no problem. Okay, those tools are not perfect. Sometimes they have false positives. Similar, but not operating on the source code, operating directly while your program is running, we have runtime code analysis tools. So runtime code analysis tools are going to be able to take care of automatically detecting or at least giving you feedback on a whole different category of potential bugs, okay? So I mentioned some of the tools that fit that category here, like Purify, Valgrind, eFence. More specifically for C programming, we are going to learn to use something called pointers this semester together. And pointers are tricky. No matter how good a programmer you are, they are tricky, especially the first time you discover them. So that means that it's very easy to make mistakes when using pointers, and the result of a mistake using pointer is a very nasty little bug that can trigger actually way after it occurred. What do I mean by that? Well, pointers are about memory addresses. So we're going to learn to do arithmetic on memory address, do computation on memory address. What happens if you try to read or write at a memory address that you computed, but you did the computation wrong? Well, you're going to read or write in a part of memory in your program that has nothing to do with the one you wanted to read or write originally. So what is the effect? What is the consequence of that? It depends. And there lies the whole issue. It depends on which part of the memory of the program you just, for example, overwrote with a bunch of zeros. Okay, if you overwrite with a bunch of zero a part of the memory of the program that is not used, no big deal. If you overwrite the content of a variable, then you're going to introduce an error, most likely in another part of the code. And this error will show up only later when you, for example, look at the final result of all of your computation. And tracking down where such error come from is very tedious, very difficult. So runtime code analysis tool help us a little bit deal mostly with pointer-related issue. It's not the only type of bug that they help us to track down, but I would say this is probably a number one motivation to use those kind of tools. Other runtime code analysis tools that are not meant to debug, but this time to do what we call profiling or optimizing. So to give you the idea of what those tools are capable to do for you and your program, I'm going to introduce the 90-10 rule. The 90-10 rule states something in the lines of 90% of the time that your program spends running, it is actually executing about 10% of its source code. So what does that mean? That means that if your program is slow, you have to be careful about what you are going to try to re-engineer, what part of your code you are going to try to rewrite differently so as to optimize the speed or minimize the amount of memory that you need or stuff like that, okay? If you are trying to optimize the 10% of the source code that's being executed 90% of the time, then every time you improve even just a little bit that 10% of the source code, you get a lot of benefits. You reap great benefits in terms of performance, memory usage, whatever you're trying to optimize. If you are trying to optimize 90% of the code that is just occasionally executed, no matter how much better you make this code, you're not going to reap nearly as many benefits, okay? Think of it about, like, let's say that I have a program that I wrote in C. This program is going to run on a server, right? It takes 5 minutes to start up. Do I want to optimize this? Well, if my program is meant to start up in 5 minutes, and then run for 6 months, a year, executing a different part of the code, I'm way better off trying to optimize this part of the code. That's going to make it more efficient rather than trying to get it to start, 10 seconds faster or something like that, since I restart it every year or so on my server, right? So that's the idea. And the tools that allow you to do those kind of optimization are called profilers. They are going to run your code, and as they run your code, they are going to keep track of how many times each pretty much line, I'm simplifying a little bit, but each line of your source code is executed. And so you're going to get very detailed statistics that are going to tell you, for example, this part of the code was never used. That's called code coverage, okay? You're going to get reports on code coverage that are going to tell you, for example, this part of the code was never used. This part of the code was used tremendously. And the profiling will help you get statistics on the function, for example, that are the most often called, how much time they spend to execute, and stuff like that. Last but not least, let's say that you have a piece of code that works, that is correct, that has been debugged. The static code analysis has nothing to report. The runtime code analysis has nothing to report. It's already been profiled and optimized. What's left to do? Well, generally, what's left to do is packaging the code. Okay, so distributing the code, you're not going to, most of the time, you don't distribute just your source code and let people figure out how to rebuild the executable from your source code. You want to give them some sort of installer, right? So in the world of Windows, we have the .msi format. In the world of macOS, we have .dmg format, for example. In Linux, we have packages, software package. There are many different formats. Two of the formats of software package that are really well known, that have been used for decades, are Debian and Red Hat Linux. So .deb and .rpm files, when you see files with those extensions, these are like software packages. There are other alternatives like Snap and stuff like that, but these are like the two that have been used like the longest, I would say. So you have to take your entire project and you have to generate your executable or executables, and you have to then package them in an installer that is going to allow an end user to easily install and deploy them on their system. Okay, so that's an overview of all the steps that I could think of in the development of even a relatively simple program. Okay, but we are going to be mostly focused in this slideshow on step number 3, which is a compiler. So let me introduce you to the compiler. What you have in the middle here is what you are going to type actually on the terminal when you want to compile a file named, for example, hw.c, stands for hello world, okay? When you want to compile a source code file hw.c into an executable file called hw, you would issue this command line here. GCC is the name of the compiler, one or more spaces, -o, -o, no space in between, more spaces, the name of the executable that you want to generate, the executable file that you want to create, and the name of the one or many source code files that you need to compile together in order to obtain that executable. And you are going to notice that we don't have .exe, okay? On Windows, when you have an executable file, it's generally suffixed with the suffix .exe. In Linux, Unix, macOS, you don't need that. Okay, there are different ways that the operating system recognize that HW is an executable file, so you can really call your executable file whatever you want. You know, HW, hw.me, hw.run, whatever you can make up. You can even use hw.exe, but the .exe suffix means nothing special to the operating system when you are on Linux. So here's an example of a source file. It doesn't do much. It displays hi on the screen. Then go to the next line, okay? So this is a syntax of the C programming language. We are going to have opportunities to dig further in the next video, okay? You use, for example, gedit, the editor that I mentioned, to edit that hw.c file on the disk. Then you go to the terminal, you type this command line, and it creates for you this executable file, okay? If we look a little bit closer, this is what would happen in a typical session. So this has been a screenshot on an older system. So some of the stuff is going to be a little out of whack there. For example, 32 bits. I don't think many people use 32-bit systems anymore. We use 64-bit system almost ubiquitously, right? So this was definitely screenshot on the older system, but the logic is the same, okay? I am in my home directory. I have a subfolder called HW for homework, inside of which I have my file hw.c. I issue the command line that I was mentioning that creates the executable file hw. I use another command line, command ls, list storage, and I give it the option -l, okay? And I ask it to list information about the executable file hw. It tells me the access permission, tells me the name of the owner of the file, the group of users to which the owner belongs to, the size of the file, and the date it was last modified, and then of course the name of the file here, okay? So I get some information to make sure the file exists on disk, and it's there, it's not empty, right? And then to run, to execute that file, I write /no space hw. And that says pretty much in the current working directory where I am on the disk right now, I want you to execute this file, hw, the file we just created, right? And it's going to run and display hi on the screen and then be done, okay? On the second screenshot here, I show you the use of another command line tool named file. If you type file space and the name of a file that's currently in your working directory, you are going to get more information about that file. For example, here, the file command tells us that hw is a elf, that's the name of the executable format used on Linux, one of them, elf 32-bit LSB executable compiled for the Intel 3386 platform, so x86 platform, and so on, so forth, okay? So this is another way to verify that your executable is well formed. So you will notice that, oops, I went forward too fast. You will notice that this is what I meant when I said that the operating system doesn't need you to name your executable .exe at the end to know it's an executable, okay? It can inspect actually the content of the file and figure out, you know, for itself that this is an executable. That's one of the differences between Linux and Windows. So we have been using the command line to compile a source code file into one executable file. We can break down this compilation in 2 steps, okay? So we have been doing all in 1 step. Now I'm going to break it down in 2 steps, and then we're going to break it down in even more steps. So at the beginning of my chain, I have my source file. At the end of I have my executable file, nothing new. But instead of, you know, issuing the command gcc-o directly, I'm going to first issue the command gcc-c and the name of the source file, okay? If I do this, then the compiler is going to take that source file and it's going to translate it, that one source file, into what we call an object file. So the term object here doesn't have anything to do with object-oriented programming, which you are going to learn about in one of the next classes, okay? It just means that this is the object that is going to be loaded in memory that you produce through the process of compilation. So my object file here has an extension .o for object, has the same base name than the source file had. So if I have a source file hw.c, it's going to be compiled into hw.o. What do I do with my object file? Not much, okay? So here I show you like the step-by-step process. I compile, generate the object file. If I do the file command on it, it's going to tell me this is a relocatable object file. So it's going to identify it as not being an executable yet, but I can apply this first process here, the stop line. I can apply it to as many files as I want. So if I have an application, for example, that is made of 23 source code files, right? I can compile independently the 23 source code file, .c files, generate 23 .o files that each correspond to one of the source files. And when the compilation works, I can then use a single command to bind together all of those object files into one executable. So GCC-O, like we did before, the name of the executable, and then here you would find the list of all the .o files. So it's a two-step compilation process where we compile each of the component of your application separately, okay? And once all of them are succeeding and have been compiling without errors, we can pull them together and generate finally our executable. So what's the benefit of this? Well, you're going to start understanding the benefits when we look at the full picture. The one step, two step was kind of like just getting our appetite. This is a real thing. That's what's happening when you run GCC. GCC is not one command. It's really a command that orchestrates the use of many different tools in order to generate your executable. So we still have here, at the beginning of this whole story, the file, the C file, the source code file that you have been editing with your editor. And we have at the end of all that processing chain, right, we have the executable file that you can then run on your system. But GCC is actually using a tool called CPP0 to transform that hw.c file into an expanded source file with an extension .i. And I'm going to explain what that means, okay? But right now we're just looking at the big picture. Then that expanded source file is going to be sent to the compiler, actually, which is called CCL, which is going to generate a translation of your source code into assembly language. Then the assembly language file is going to be sent to an assembler, AS, which is going to translate it from assembly, which is still human readable, to an object file, which is binary. And then all those object files are going to be collected by the linker, LD, and that are going to be used to form your executable file. Okay, so there's a lot involved in the compilation steps. What is the advantage of having everything broken down like this? Well, if you are working on hw.c, right, I need to translate it into hw.i, then hw.s, then hw.o. But then I can find on disk a bunch of other .o files that are already pre-compiled, and I'm going to just like add them alongside your new .o file and generate the executable. Or even better, I can use standard libraries, okay, generally located in the folder /usr/lib. I can use standard libraries that are already written by other programmers, etc. They just give me the .o file, the libraries, and I'm going to link them with my own .o file and get my executable. Okay, so that makes for a very modular approach to constructing software. So now, let's take a look a little bit more in detail. So the first thing I would recommend that you do is man GCC, just to take a look at the magnitude of if anything else, the magnitude of that man page, right? But out of the man GCC, these are the options I want you to be aware of. So not much, okay? Just 3 options. When you use GCC, you can say things like GCC-C, and then you would say hw.c, right? And if you do that, it's going to generate only hw.o. If you use the -s, uppercase S option instead, it's going to generate the hw.s from your hw.c. If you use the -e, uppercase E again, it's going to generate only the expanded source file from your source code. So we have a way when we use the command line, in case things go wrong or in case we want to or need to analyze in more detail, what's going on, we have a way to tell GCC, don't do the whole processing. Stop after a certain step, okay, and show me the results. So we can inspect what the hw.i, hw.s, hw.o file contain, okay? So let's go over those steps and add like the final comments I have to ask over each of them. Let's talk about the first step. So the first step is referred to as precompiling, the tool that takes care underneath the hood of doing the precompilation is called CPP, C preprocessor, okay? And it's going to focus on lines of code that starts with a hashtag symbol or pound symbol, okay? So when I write something like pound include stdio.h, okay, this is part of the C syntax, but because it starts with a pound symbol, it's more specifically a syntax that talks to the preprocessor, okay? And the C preprocessor is going to, for example, take all of those lines that have a pound include followed by the name of a file, right? And it's going to replace them, like if you did cut and paste, by the actual content of that stdio.h file. So this is why we call it an expanded source file, because I have the code that I wrote here, okay, it's still there, and then each of those pound include precompiler directive, as we call them, are going to be expanded into the actual content of the file that we are trying to include in our source. And now we have this hw.i file, okay, with all the include statement resolved. And include is not the only thing that's going to be resolved, okay, but this is the one that I'm using for this introductory example. All of those pound includes statement that we had are going to be resolved and the corresponding code added to my source code. And now it's ready for the next step of compilation. The next step of compilation is the actual compilation. So I have my hw.i file. The CCL compiler is going to actually take all of that source code, including the part that I wrote and the parts or parts, plural, that were included with the pound include directive, and it's going to translate that into assembly. So here's an example of what assembly language for the x86 family of CPU would look like. It's still human readable. You can program by hand in assembly. Less and less people are interested in doing so, I think, as we tend to go toward higher and higher level languages, right? But it's still human readable. It's just a more machine-friendly language in the sense that it's easier to then take this, okay? Once we have done this pre-translation from C to assembly language, it's easier to take the assembly language and then generate, the object file that correspond to that, the machine code that correspond to that. So we do this intermediary translation just to make it easier to do the final translation we need to do. And then this final translation is going to be done by the assembler. Okay, so this is yet another tool that's going to take source code written in assembly and it's going to generate for us those relocatable objects, as they are called, those .o file that are going to be then taken all together and pieced together to make actually your executable. And that last step is going to be the job of the linker. In our case, it's going to be the command LD. And the linker is going to take one or more, actually, of those object files, okay? All the object files that constitute your application, all the libraries that you are including, all of the other part that other programmers, the team contributed, put them together and stitch them together to form our executable file. So just out of curiosity, I pasted here the actual command that was used by GCC when it calls the LD command to do that linkage, okay? So there is a lot of stuff here that we are not going to look into detail, but here's the option that says this is the name of the executable I want. Here's a piece, one of those relocatable.o file, okay, that we didn't write. It's called crti.o. Here's another one. These are going to be kind of stitched together at the beginning of the executable, okay? Then we are going to have library code. So library code. Then we are going to have our own code, okay? And then we are going to have, again, CRT end here and CRT end.o. And those CRT-I, CRT begin, CRT end, CRT end. They stand for C run time. So it's a part of the code in our executable that sets up everything so that our code can be executed properly on the operating system, right? So we don't have to write that. It's already there. It's already available. It's somewhere on the disk. Okay, you can see the path names there if you're curious for this old version of Linux I was using. And then we can go just fetch the .o file and ask the linker, put them together with our own .o files, and then we get the executable. So we're going to wrap it here for this presentation. The goal here is not to inundate you with detail, but it's to start getting you an idea of what is really happening when you click that button that automatically, for example, execute your Python program, right? So this is going to be the theme for the whole semester in this course. We want to do a lot of the things that you already did in the prerequisite course. We want to redo them again with C, but because we are using C, and C is a much lower level language than, say, for example, Python, we are going to expose you to all of those details and progressively build your understanding of what's going on when you write code, when you run code, when you compile code at a much deeper level. All right. As usual, thanks for your attention, and I'll see you in the next video.